Thank you again for having me, and thank you for the introduction. My name is Thallner. I am a postdoc at the University of Florida, and I'm working together with Courtney Sprain, Juliane Danberg, and Renee Gassmüller here at University of Florida on trying to figure out what mantle convection, what effects of mantle convection we can see in the magnetic field on the surface. So we're doing this together with Richard Bono, Chris Davis, Domenico Midori, and Andy Biggin, who are our collaborators mainly in Europe. And as you will see in the upcoming slides, I'm neither a mantle modeler nor a geodynamo modeler. I'm a paleomagnetist. So my main concerns is what can we actually see in observable data. So for the motivation of this project, we actually looked a lot at magnetic field strength and the variation of magnetic field strength through time. And you can see that here on the left. One thing that you can immediately see is that the data distribution is not great the older our rocks get, and that will be a part of why the whole process is quite difficult and why we need numerical geodynamic simulations to help us out. So we are using trends that we can see in this intensity record. But when I say trends, it is not trivial to actually see trends. It often depends on who you talk to about which trend you're going to see. And that is true the further back in time we get. We have a pretty good idea of what the field variation was doing in the last 2 million years. And we have less and less of an idea the further back we get, especially after we get into the Precambrian. It's a bit of a free-for-all, but that doesn't mean that there's no important information in this record. For example, very low field strength estimates around the Precambrian-Cambrian transition are now kind of our big support for a young inner core formation around this time. And in addition to the field strength, we, of course, also look at reversal frequencies. They are somewhat related with higher field strength in time periods with lower reversals and the other way around. And we can see, looking at this picture, that the time intervals between supercrons is somewhat similar to the time it takes for the convective overturn in the mantle. So that was a big part of why we looked into mantle convection in the first place. So looking at our workflow, I'm also not a graphic designer, but it shows really well the kind of circle that we are going from data back to data. So we are starting with paleomagnetic observations. First, these are being used to get our global plate reconstructions that then drive our 3D mantle convection models, which link what's happening at the surface with what we can see at the core mantle boundary. And by we, I mean the geodynamo, because that is directly affected by these changes in core mantle heat flux due to the convection. And from the geodynamo simulations that we run, we can once again get pseudo paleomagnetic data that we can then statistically analyze and compare to what we actually see from measurements of historic field strength data. And these comparisons are what inform us about if both our mantle convection models or our numerical geodynamo simulations give us a realistic estimate that is comparable to what we can measure. And with that, we can make inferences on what has happened in the deep earth. So this is not entirely new. It has been done before, and people have used heterogeneous boundary conditions on geodynamo simulations to see what is going on the surface. We can see here the influences on reversals, but also on the dipole moments, field strength. And usually that has been done using simple geometric patterns, but it has also been done using output from mantle convection models. For all of the studies where this has been done, the time frame is usually cut off somewhere around 300 to 400 million years, and that makes sense just because the plate models are associated with high uncertainties before that. But what we are going to do still is we're going to make this time frame longer and look at a billion years to try and get an idea of what changes we can see in the core mantle boundary throughout a supercontinent cycle. I'm going to start at the mantle models. So these are really the work being done by Juliane Dunberg and René Gößmüller. I am going to give a brief overview about the models that we had. If you're interested in details, they have recently been published. So I've posted the name of the publication down here, and have a look in there. There are all the details. So what we are doing is we are running 3D global convection models with the software Aspect. I don't think I need to explain to anyone here what Aspect is. What it's doing is we are creating space and time dependent boundary conditions for temperature, velocity, and composition. We are computing material properties using the thermodynamic modeling software Perplex and the thermodynamic database. And we use a temperature and depth dependent viscosity model based on mineral physics data to include the effects of both the convectional variations and mineral phase transition on buoyancy, heat transport, and volume changes. Down here at the bottom right, I have a small table of different models that we have run, and I'm going to come back to that in a bit. But what I want to show on this slide is the plate reconstruction that we have used. So we are using the reconstruction for the last 1 billion years based on the study by Meredith et al. And as I said, everything further back than 300 million years, definitely further back than 500 million years, there are high uncertainties associated with that. So keep that in mind, that we are maybe not creating the perfect time series of what's going on in the mantle and at the core mantle boundary. So we have run these models for a billion years, and you can see here already the slabs going down from the surface after being subducted, and at the bottom we have the thermochemical piles at the core mantle boundary. I think it's a bit better visible here. This is a visual representation of the mantle convection model with slabs in the gray to bluish color representing pressure, and slabs have been defined as these as the regions that are at least 200 Kelvin below the adiabatic temperature, and they are only shown below the 660 transition zone. What you can see here are the interactions with the thermochemical piles. These are the regions with the basalt fraction of larger than 0.5, and they're shown here in the yellow to reddish colors that indicate the pressures there. The other thing that you can see here is the computational mesh of the model that has been used. You can see that in the bottom right quadrant here. And you can also see the boundaries of the model. The outer boundary is shown in the gray sphere, and the inner boundary you can see in a dark yellow at regions where we don't have any piles. So it's a bit difficult to see, but this is really the area that we are interested in, because we really want to see what's happening at the core mantle boundary. So the way that looks like is shown here. I'm showing 5 different models that have been run in the study. At the far right, we have the plate reconstruction that is driving the whole thing at the surface. And I'm showing one slice of the core mantle boundary heat flux density for each 100 million year step. So the first 2 models are the thermochemical and the thermal model. These have been run with a constant thermal conductivity of 4.7 watts per meter Kelvin, and a thermal conductivity profile from Tosi et al. For the region above 660 kilometers, and Stackhouse et al. For the regions below. The other 3 models have been run with pressure and temperature dependent conductivity, and for the 2 models on the right, we have added additional rheologic complexities. first one here, that's called weak post-perovskite. We have reduced the viscosity of the post-perovskite phase by a factor of 100. And for the strong basalt model, we've increased the viscosity by a factor of 10 for the basaltic material. And what's really interesting to see here is when you go all the way down to the last time step, because this is really where we can see how realistic the end member of our models are, because this is where we can compare it to real data from seismic tomography. So here I'm showing the last time slice of each model again, compared to a slice of seismic tomography. So the modeled maps show temperature distribution as a difference to the initial Mantle adiabat, and all of those slices are in 2,600 kilometers depth at the very end of the simulations. The negative values of the seismic velocity anomaly that you can see here in red are also plotted on top of the modeled maps in yellow, just to get a better comparison between the modeled temperature anomaly and what we can see from seismic tomography. And with the exception of the purely thermal model, I'm going to mostly ignore this for the rest of this talk, we can at least see hints of the degree 2 structure that we can see in the seismic tomography, with the colder regions below the slabs and the hotter regions where we suspect the LLSVPs. And we can look at this also in a different way. So these plots show temperature distributions, again shown as different compared to the initial Mantle adiabat, but now in an equatorial slice at the end of the simulations. The inlets that you can see in each of those slices are showing magnified versions of one upwelling and one downwelling near the CMB, usually from the top here. And the arrows, which I think are a bit difficult to see here, they show the flow field. And on the right, we can compare this to the same slice, showing once again S-wave velocity differences for the same slice. Going forward, I am going to focus on the thermochemical model. This has been the reference model in the published study, and I'm going to come back to it a bit why we are going to use it. But before, I've shown just slices at 100 million year steps. This is what it looks like if we show an animation of the whole 1 billion years. So we can see at the beginning, after almost 200 million years, we can see the first slabs reaching the core mantle boundary, and we can follow the evolution through the whole 1 billion years. What I forgot to say at the beginning, we are using a paleomagnetic reference frame for all of our models. And this animation, we can look at this in a different way by looking at the power spectrum of the maps that we are looking at. And when we do that, for the first 4 spherical harmonic degrees of the heat flux, then we can see at the present day, we see degree 2 dominating, as we would expect, but it changes throughout time. We have a small time period where we have degree 1 quite strong, and a large amount of time where we have a degree 3 structure. And based on this plot, similar plot like this, we decided to take peaks in the spherical harmonic power spectrum to give us time periods that are going to be interesting for us to look at. So what we will do is, or what we have done, is we take snapshots of the core mantle boundary heat flux at these specific times and use those as boundary condition for our geodynamo models. When we look at the total heat flux out of the core, here it is plotted for all the models that we have run. In gray, you would see a reasonable range for Earth, and the thermochemical model is really the one that gives us the most reasonable value. So this is one of the reasons why we have used it. Since we want to tie it all to magnetic field observables, we tried a very simple way of doing that, and that is by looking at both the total heat flux out of the core and the equatorial heat flux density, which is just the heat flux in a 30-degree latitude band around the equator. And we compare that to occurrences of supercrons that are shown here in green, and hyperreversing times of the magnetic field shown in purple. And the purple fades out after 500 million years because our data is really not good enough to say anything. But important here is there's no real correlation visible from plotting these against each other. So we really need to go into the geodynamo and have them help us with that. For the geodynamo simulations, we are using the code of the University of Leeds. We are using the exact setup of Mound and Davis 2017, Midori et al. 2021, and some of those models have also been shown in Sprain et al. 2019. So at the moment, we have over 200 simulations that we've run so far. We are using a range of Ackermann numbers somewhere between 1 e to the minus 3 and 1.5 e to the minus 4. We are letting our models run for a minimum of 1 magnetic diffusion time. Ideally, or most of them have been run for 2 or more magnetic diffusion times. And the first thing that we have looked at is the present day case, because this is where we have the best data. And we wanted to see if it even makes a difference if we switch from tomographic, from a heat flux pattern based on tomographic data, as here in Mound and Davis, if we switch from that to something that we get from aspect. So to do that, we had a look at something that Mound and Davis 2017 had already looked at. And what they did is they used this pattern and they scaled the heterogeneity. They scaled the amplitude of heat flux anomalies and looked at the differences. So we did that as well. And for that, I'm going to reference something a lot in the upcoming slides. We have the parameter Q star that defines this heterogeneity for us. It's not very complicated. It's just the maximum heat flux minus the minimum heat flux over the average. So what that means is the larger the difference between the amplitudes of heat flux anomalies, the higher value of Q star we will get. So a Q star value of 0 would be a homogeneous boundary condition. The heterogeneity increases with Q star. In red, I'm plotting Q star values that we see from our aspect model, and you can see they stay in a reasonable range between 2.5-ish up to 5, and these are really the values that we have used there. So first step, as I said, is we are going to take tomographic heat flux pattern based on tomographic data. I'm going to refer to this as our tomographic map, and same a present day output from our thermochemical model that I'm going to refer to as the aspect map. And you can see right away from the heat flux distributions that there is quite a difference between those two. So we do expect a difference on the geodynamo. So what we've done is we've taken 15 geodynamo models from previously published publications. And the only thing that we changed for them was, for each of them, we changed the pattern that we use. So we run the same model again and again and again and change the pattern. We use tomographic and aspect patterns, and then we scale both of these patterns to have comparable values of Q star. And what we then want to look at is how can we see this on the surface. So for all non-paleomagnetists, when you think about paleomagnetic data, then what we think about is really polar wander paths. And that's fine for recent times, but when we go further back in time, like millions of years, all we get is a bunch of data that is more difficult to correlate. But what we can do is we can look at the dispersion of these virtual magnetic poles, or VGP, and describe them with the factor S standing for scattered. So both of these would represent paleomagnetic data of one locality. And if we take a global data set as the PSV data set from Cromwell et al. 2018 here, then we can see that the dispersion is dependent on the latitude of the site where it has been measured. And this has been described with model G, which is just a simple quadratic fit with the two parameters A and B, where A just gives an estimate for what the average dispersion of VGPs at the equator, and B describes the change with latitude. B is usually very unconstrained, but A is important for us because it can be used as a proxy for axial dipole dominance of the dynamo, which has been shown in beginner of 2020. So the way it works is we can take a geodynamo model and treat it like a paleomagnetic data set. And when we do that, we can define these model G parameters. And you can see here the increasing axial dipole dominance in these three models. You can see the decreasing values of model GA and how these relate to the ratio of axial dipole to non-axial dipole power. When we do that for our models, what I'm showing here and in some of the upcoming plots is on the x-axis, we have increasing values of heterogeneity, and on the x-axis, we have the values of statistical estimates for field observables that we see. In this case, model GA and model GB. In blue, I'm showing the homogeneous boundary condition and compare this to more and more heterogeneous heat flux. In red, I am showing the range of results for models using tomographic map. In green, same results for a map from aspect. And I'm plotting these next to each other, but they are using the same value of Q star every time. When we look at the VGP dispersion at the equator, we can already see that there are big differences between tomographic and aspect. When we look at the tomographic data, then we can see that the VGP dispersion increases massively by increasing the heat flux heterogeneity, which is not the case for simulations using the aspect heat flux. For B, it's not really obvious what is going on, but as I said, it's usually badly constrained, so the focus would be on A. But that's not the only thing that we can look at. We can also look at inclination anomaly, which is the difference in inclination that we can see compared to the geocentric axial dipole field model, GAT model. And here we can really see the first really systematic changes for both tomographic and aspect boundary conditions. And both of those show increases of inclination anomaly with heterogeneity, but it's less of a factor for the aspect simulations. We can also look at reversals. We have defined those as the relative or proportional transition time, which is just the relative time that the dipole of the dynamo spends within latitudes of plus or minus 45 degrees. We can once again see the differences. Most of the aspect models stay at or close to zero, which basically tells us that way fewer models using aspect boundary conditions reverse compared to a tomographic boundary condition. We can also look at field strength. The way we would do that in the surface with a limited amount of data is by using a factor called V%. That's looking at virtual dipole moment distribution and takes the interquartile range divided by the median value. So low values of V% are usually associated with high fields and low variability, and on the contrast, large values of V% are usually associated with weak fields. And we can see small differences here. The fields that are reversing more as the tomographic ones. For the higher values of Q star, we see lower field strengths as expected. And all of these paleomagnetic observables basically are just proxies to tell us something about the dipolarity of the dynamo and also about the balance of magnetic over kinetic energy. And we can especially see with the dipolarity that aspect models stay closer to the initial value when we increase heterogeneity. But to figure out why, we tried to see if the small scale structures in the models have anything to do with it. And we have truncated the maps that come out of aspect to maximum circular harmonic degrees, 16, 12, 8, and 4, and run the same models again with these maps. And for some of the simulations, we can see large differences for dipolarity, energy balance, the VGP dispersion, and transition time for some truncations, not for others. But for the majority of the models, there's not much happening. And we can see that even better here, where I plot the values of aspect versus the truncated values. And you can see most of the values plot at the unit slope, indicating that there is not a lot happening. And the changes that we do see are very, very subtle. And the last thing that I want to show is going back to what I said at the beginning. We, of course, want to see what the different patterns due to the geodynamo. And if I'm doing the same thing as I did before, then for all of the observables, and I should really say this is very early and I will have to spend a lot of time looking at this data, but I see much less variation due to the different patterns than I see because of changes in heterogeneity or in amplitude of the heat flux anomalies. And that's quite different uh, from what we expected. But if that holds true when I'm done with the analysis and all the models have finished running, then what that means is that we would have a really difficult time to spot these changes in pattern in the magnetic field on the surface. And I'm going to stop here. Our first preliminary observations is that the small scale features of CMB heat flux really seem to influence some of the dynamos. I have not found a systematic reason for why it affects some and not others. And we can see trends with heterogeneity that are much larger and more systematic than trends that we can see due to different patterns. But all of these trends are more pronounced when we use a tomographic pattern for heat flux compared to one out of the Mantle models. But we are far from being done. We still have to expand the parameter size space of our simulations. We are running some models that also vary in the core size to see the effects of that. And since all of our models, all of our geodynamo simulations have been purely thermal simulations, bottom heated, and we haven't done a co-density approach yet, that is going to be one of the next steps that we still have to do. And I'm going to stop here because I'm really out of